8:30 p.m. Eastern Time will be when they open up. And this upcoming Tuesday, there will be one quiz 0. This is going to be unmarked. It will be simply to help you practice your math skills. I will quickly double check. Yes, this Tuesday, quiz 0 is going to be on CrowdMark. It'll be ungraded. It's just to make sure that you're familiar with using the mathematics of the course.
All right, thank you. Appreciate it.
You're welcome.
Okay, hi everybody. How are you doing?
I'm great. Keeping them entertained. I haven't started telling funny stories about you. You just showed up, so.
Well, that's a good thing, or not. Yeah. Well, thank you, everyone. And I know I'm very sorry that the first class got off to such a rocky start. Hopefully, I mean, we're doing everything we can to make sure that won't happen again. To answer a number of questions we got today, we will give information about posting PDF files of the lectures. It looks like it's going to be done in Top Hat, and you will be able to download them from there. The idea is to minimize the number of platforms that you have to use, and that we have to use. So I haven't had time to upload them today because to the extent I've had any, I've had to deal, and Matthew and Samana, the three of us have had to deal with the technical issues with IT that have come up, and we're still in discussion with them. If you want to know what happened, basically what happened was the online assistant was given permission for enough people and enough time, but about 2 minutes before the class, the university took it away from him, and he didn't know it, and neither did any of the rest of us. And why they took it away, of course, is the issue. But in any event, I believe now we have a limit of 500 and unlimited time. I see that, I guess it's Martina has a question.
Yeah, I actually had a question about one of the assignments that you posted on Mobius. I think it was like assignment 0. If I could ask that now, I can also ask that at the end if that makes.
Okay, Matthew, do we have an assignment 0?
Yeah, it's just for math practice. I'm happy to entertain the question now, or if you want to get going, Rob, I'll stay on afterwards.
Yeah, can we postpone that, Martina?
Yeah, that's fine.
Okay. So we do have, I see a number of things coming in the chat, and our online assistants are going to do the best to answer these. Most of these questions they can deal with, but they do flag questions, and those that they can't deal with will go up the chain, and Matthew, Samana, and I will deal with those questions. Keep in mind, none of us can really give a class and answer what are literally dozens of chat questions at the same time. So I want to pick up where we left off. Just to do the attendance part, the code is 9797. I'll start sharing my screen now so that you can see that number. You should all be able to see it. So why don't you log in and do that?
Excuse me, Professor. I just have a question.
Yeah, sure.
Are we able to download the PowerPoints before the lecture so we can take notes as we go?
You will be able to see them. I don't know that we'll have them downloadable until after the classes. Why do you need them beforehand? You said, but I missed it.
It's just easier to take notes. I can write over the PowerPoints as the class goes on.
Okay. We'll consider that. The one disadvantage, perhaps for you, in doing that is that if there are typos on the slides and so on, they might be there. and you might be misled. On the other hand, if there are typos and you spot them, and then maybe you learn something. So we'll look into that. I guess my thought was that you would look at it online with the textbook, but let me oh boy, take a poll by popular demand. How many of you how am I going to do this?
I think there's a polling button at the very bottom of your screen, next to the share screen button. You can create a poll that way.
Okay, I'm going to stop sharing for a minute. But I'm not. Where is this polling button?
It should be next to the share button. The alternative is to have people go to reactions and click the green check mark.
Well, that's what I was going to do, but a poll is a bit easier, but I don't see any polling button on my thing. Where do you think it is?
Should be next to the share screen button, but if it's not there,
no, what's next to that is record.
Oh, well.
All right.
Yeah, I don't have it either.
Yeah, okay. Well, let's do it this way. If you want the PowerPoint things to also be in downloadable PDF in advance, put a thumbs up in your picture.
Sorry, Professor, would you mind repeating?
If you would like the slides to also be in PDF form prior to each class so that you can download them, put a thumb up.
Thank you.
Okay, the trouble with these thumbs is they don't last. So I'm seeing some people in the class want them. It looks like enough that I guess we'll have to go along with that. So, okay, we'll look into that. All right. So let me get back to where we were. So we've got, I guess, enough people. We've got a quorum, so I'm going to keep this open and get going. So where were we? So I went through this a bit fast. The idea of dimensional analysis is that you can check formulas by checking dimensions. Every term has to have the same units. If it's length on the left side, every term on the right side better be a length. If it's a force on one side of the equation, it better be a force on the other. So that's what this thing here was about. Intuitively, we would expect the force on this satellite to go like the area of this thing right here, of the solar panel. More area means it'll have more drag force. If the atmosphere is denser, then we also expect there to be more force. And if it's moving faster through a fluid, we also expect that. Well, how much, right? Well, we don't know, so we write rho to the A, V to the B, A to the C, density to some exponent, velocity to some exponent, and area to some exponent. And then knowing the units of these quantities that I flash up here, we plug these values into this relationship. And I know force is a mass length per time squared. That's the left side. That better be the units of the right side over here, which is m over L cubed to the A, L over T to the B, and L squared to the C. And once you have this, you can simplify. The L's all have to combine, so you get L to the B plus 2C minus 3A, T to the negative B, and M to the A. It's pretty clear that A had better be 1, and B had better be negative 2. B had better be positive 2, I mean, to get the minus 2 here. And then the sum of these three, the exponent in L better equal 1, which is this exponent here, and that means C is 1. And so we end up getting a formula, rho v squared times a. And the only thing we don't know is what the coefficient has to be. That is something that has to be determined from a more fundamental understanding. But this is a very reasonable formula for the drag force. Yes, question?
Yeah, at the starting of the slide, you said that on both sides of the equation, something has to be the same. Can you repeat that on my...
The units, the dimensions. The dimensions on the left are mass times length over the square of a time, because that's mass acceleration. The units on the right, therefore, better be mass acceleration or mass length per time squared. I'm forcing the units of this to be the units of that. And that's what gives me this answer right here. So dimensional analysis told us this answer. So to make it an equation, instead of a proportionality, I have a constant that depends on the shape of the object and other things. We call it the drag coefficient, and I don't know what that is from dimensional analysis. It doesn't have units, so I can't figure it out. In the real world, its actual value would depend on difficult to solve hydrodynamic equations. But you get a lot of basic physics, namely the rho v squared a, simply from dimensional analysis. Now in the course, we won't do things that are quite as sophisticated as this, but I have seen many a student get an answer wrong because they incorrectly wrote an exponent down in an equation they knew and messed things up. And if they had just taken a bit more time to check the units, they wouldn't have made that error. For example, kinetic energy is 1/2 mv squared. I'm able to write a little bit on this crude thing here. So the kinetic energy, we call it K, is 1/2 the mass of the object, as we will see later in the course, times the square of the velocity. Now, sometimes students have forgotten the square. It's just a silly error, and they get the wrong answer. Had they only taken the trouble to check the units, they could have avoided that. So that's an example of how dimensional analysis can be used. So is that okay?
Yep, that's fine.
All right. So next here, where are we? We're going to say a little bit about estimates, and then I'm going to go to vectors. Now, often in physics, we meet situations where we don't have enough information to compute a precise value, but we can make useful approximations. These approximations or estimates involve reasonable guesses for the values of unknown quantities or probabilities and some dimensional analysis. And Enrico Fermi was a person who used this a lot, and now these kinds of problems are called Fermi problems. So here's an example. An order of magnitude estimate of a quantity gives you a rough idea of its magnitude. So, for example, you don't know the income of your other classmates, but based on your own income, you could probably make a good estimate as to what your classmates' incomes are, or the parents of your classmates. And you won't get the number right, but it's pretty clear the parents of your classmates are making more than $10 a year. It's also pretty clear that they're making less than $10 billion a year. So if you think about that and can narrow it down, you could probably make a good guess within a factor of 10. So that's the idea of an order of magnitude. Now here is a picture of a human brain in profile, and we could ask how many cells are in a human brain. And we can ask how much such a thing weighs. Now you might think, how the dickens am I going to do that? Well, you need a little bit of information, but let's see how we could make this kind of estimate. What do you think we need to know to be able to do? Oh, sorry, Daniel's got a question.
Can I make a guess for the weight?
Well, you could. I was going to give a bit more. How much do you want to guess?
I want to guess 5 kilograms.
Okay, let's keep that in mind. Mario.
I was just wondering that order of magnitude basically means it's an approximate estimate between a certain range, right?
Yes, that's right. So, what do you think we need to know in order to estimate the number of cells in a human brain?
The average size of a human brain?
Yeah.
The
And
size
how would,
of the
Like the volume?
the size of the cells?
well, and the size of the cells, right? So we know roughly the volume of a human head, we could guess it, and we would need to know roughly the size of a cell. So here we have it. A red blood cell is about 10 microns in size, 1 times 10 to the minus 5 meters, and the mass is about 10 to the minus 13 kilograms. Now, how big is a head, roughly, in meters? Hint, use your head.
Like how big is the head?
Well,
Like
yeah.
1/10 of a meter.
I don't know if you said hand or head. That's why.
Head. And I've muted everybody to get rid of echo, so if you want to talk, you'll have to unmute yourself and then mute again. Hassan, what do you say?
I say like around like 8 inches. In volume, you mean?
Well, yeah, but how would you estimate the volume of a head?
You'd assume it was like a perfect circle. So then
That sounds good, or not a circle, but a perfect
oval.
Sphere.
Sorry. Oh my God.
We don't live in flatland. Actually, I can see why you made the mistake, because right now we all do live in flatland. You're all two-dimensional people to me, but yeah, the volume of a sphere. And how big is that sphere, roughly? In meters.
Diameter of about 0.1 of a meter.
Yeah, something like that. Maybe 0.1. If it's got a diameter of 10 centimeters, then we could get the volume, right? So the volume goes like 4/3 pi r cubed. Pi is about 3, so we've got about 4 times the cube of 0.1 in meters, and then we would have to divide by the volume of the cell. So let's see. The size of the brain, very good, about 0.1 meters. The volume of the brain is therefore about 10 to the minus cubed meters. Forget about the 4/3 pi. The size of a cell is about that. The volume is about the cube of that. So how many cells are in the brain? How would we figure it out? We would have, what's your guess based on this? We have this much volume that's got to fit in there, so how many cells can be crammed in?
So the volume brain divided by the volume of cell.
Yeah.
10 to
What's the number? Sorry, somebody said it. What is it?
10 to the 12.
10 to the 12. Well, let's see. What is it? It's 10 to the 12. That's right. Before telling you the real answer, let's do the weight. So again, the size of a brain and the volume is 10 to the minus 3 cubic meters is about 1,000 cubic centimeters. The body's mostly water. Water is a gram per cubic centimeter. So the mass of the brain is about 1,000 grams. And the density, so that's about a kilogram, right? That's the weight of a brain. Now, what's the real world? Actually, 10 to the 11. So we were out by a factor of 10, which is pretty good. A real brain has about that many cells in it. And the weight of a real brain is about 1.3 kilograms, not 5. But 5 is in the ballpark. So this is how you do these estimating questions, and the way you'll use them in this course is primarily when you look at an answer, does it make sense? So for example, if you get a problem like someone throws a rock off a building 100 meters high, what is the velocity as it hits the ground? Well, if you're getting 10 to the 10 meters per second, you probably made a mistake. Just think about it. Real things won't move that quickly. If you're getting 1 micron per year, probably you made a mistake. Now, I'm exaggerating, of course, but the use of these Fermi problems is for you to try and estimate whether or not your answers make sense. So, here's the summary of what we did in Chapter 1, and I'm not going to go through it here. We basically did just precision, accuracy, and dimensional analysis. And so, what I'm going to do now is end this and go to the slides in Chapter 2, because that's what I would have done in the remaining part, and we'll spend some time on that. And I've got to unassign these to everybody, okay? So let's just start this presentation. This is about scalars and vectors. Now, I'm assuming all of you in high school have seen a vector, right? You know what it is. It's a quantity with magnitude and direction. A scalar is a quantity that has magnitude but no direction. So mass is an example of that. The mass of an object has magnitude, but it has no direction. Mass doesn't point anywhere. But if you're at the end of the cliff and someone shoves you, you might care about which the direction of the push is. And so you can make a list of quantities that have a direction and a list of quantities that do not have direction. So before we go to the next slide, maybe some of you say it. What kinds of quantities have magnitude and direction? Anybody? Velocity. Yep. Force, right? Okay. Momentum, very good. All right. What are some quantities besides mass that have magnitude but no direction? Speed. Speed. Charge. Good. Very good. All right. Got the idea. So these are the goals, Chapter 2, to understand vectors, scalars, vector components, unit vectors, dot product. And I'm going to go through this rather quickly because I understand it be review material. So suppose you're on Ottawa and fly for 6 hours at 500 kilometers an hour. Where will you be? Well, the answer depends on which way the plane is going. You might be in Greenland, or you might be in Cuba. Because those are outer limits of where you could get from Ottawa without the direction being specified. You might get Yellowknife, you might get to Haiti, you might get to Newfoundland, who knows? Well, you'd be on the ocean. So, as we've already heard, somebody said that speed was a scalar, that's right. Velocity is a vector. And we've already seen someone else said temperature is a scalar, that's right. So this is just repeating what I said. Scalar refers to things that have magnitude only. Vectors have magnitude and direction, like velocity or momentum or force. And in two dimensions, you can draw pictures of these things, also in 3, but it's a bit more awkward. You usually use arrows. The magnitude is represented by the length of the arrow, and the direction is where the arrow points. The head of the arrow tells you it's going this vector of 30 meters per second is that way. This other vector is shorter, it's half the length. 15 meters per second, but pointing in a different direction. So we usually, we already can see where the information about a vector is. Here's the magnitude 30, and the angle relative to the x-axis tells us what the direction is. Vectors can be described in terms of their components. Now I'm hoping you've all heard of components and seen them a bit. Is that right, basically? Good. Yeah, I see some of you nodding your heads. So we find the components by projecting. And if, let's say this vector is 25 degrees relative to what we call the x-axis, then its x-component is its magnitude, v, times the cos of 25 degrees, and its y-component is its magnitude, v, times the sine of 25 degrees. So to find the components, project along the axes. So here's a little quiz question for you. A force has magnitude of 50 newtons and is directed 30 degrees counterclockwise from the x-axis. Which of the answers below is closest to the x-component of the force? I haven't opened the question yet. 50 newtons in magnitude, 30 degrees counterclockwise from the x-axis. What is closest to the x-component of the force? 8 newtons, 25, 43, or 50? Go. Text 0571 and your response to this number. Since some are having trouble getting in, I'll add a little bit more time. Okay. Okay, well, pretty much everybody answered. Responses. Some said 8, some said 25, one couple said that, but the correct answer is what the majority got. It is 135. The reason for that, the way you do it in your head, is you need the cosine of 30 degrees. So the vector, if I can annotate this for a bit, the oopsie daisy, the vector is pointing up like this, and it's at 30 degrees relative to the x-axis, which is here. So you need the cosine of this angle, which is 30. Now, the cos of 30 is a good thing to memorize. It's root 3 over 2. So root 3 over 2 times 50 is 25 times root 3. So the first two answers are wrong, and you know it can't be 50, so there's only one left. Okay, so let's continue. Vector components, x and y, are given by v cos theta and v sine theta, where theta is the angle relative to the x-axis. So if you know the angle and the magnitude, you know the components. Conversely, if you know the components, you get the magnitude from Pythagoras' theorem, the square root of the sum of the squares, and you get the angle by the tan of the angle by dividing the by taking the y component and dividing it by the x component. If you know the angle relative to the y-axis, then this flips around. Vx is v sine of theta star, and vy is v cos of theta star, and it works the other way around. I almost never do the bottom thing. I find it confusing. I just always do this kind of thing. Okay, how are we doing? Any questions?
So, Professor,
Yeah.
instead of doing the bottom part, you can just use the top part, but just use the other angle, right?
Well, if you know the angle relative to y, just subtract it from 90 and you'll get the angle relative to x, and then you can use the top formula. That's what I do. But some people might be clever at using the bottom and top interchangeably. But, you know, don't get confused, right? It's like in Star Trek, a phaser has two settings, stun or kill. Try not to get them confused. All right, here we go. So there are if we want to add vectors, which will be very common in this course, there are two ways of doing it. One is the parallelogram rule, where you leave the vectors the way they are, but then draw a parallelogram. In this case, that happens to be a square, but basically draw a line perpendicular to one and parallel to the other, and then vice versa. And then the line that goes from the tails of both to the other side of the parallelogram is the sum. Personally, I find this rather awkward. I like to move the other guy and go tail to head, tail to head. So my favorite way is the bottom one, but again, different people have different choices, but my preference is the triangle construction rule. So if this person here had forces F1 and F2 on them, basically this person has got a force going upward, and if there's nothing holding them to the ground, up they go. So I just said what the parallelogram rule is, so I won't go through that detail. For the triangle rule, all you do is slide one vector along the other so it maintains its same direction and magnitude, but you just put the tail of one by the head of the other, and then the final vector is given by just drawing tail to head, tail of the one guy to the head of the other guy. So I'm not going to go to this PhET, as they call it, this simulation now where you add vectors. But if you want to get this later and copy this URL into a browser, you can have fun playing with adding these things. But I'm guessing most of you have done vector addition when you were in high school. Am I right about that? Yeah, okay. Mario, you seem to have another question.
Oh, no, I forgot to put the hand down.
Okay, all right. All right, let's continue. Now, the way I like even better is the algebraic approach, where you resolve the vectors into components, and then you add the components pointing on the same axis to get the components of the final or the resultant vector, as it's called. So, for these three vectors, I can resolve F1, F2, and F3 into components, and I just add up the X components, positive or negative, depending on where they're pointing. I add up the Y components, and then the final vector is simply given by the component sum of each. So here is an explicit example. If I have F1 plus F2 plus F3, as in the previous thing, here's the resultant vector, and the sum of the X components of 1, 2, and 3 is the X component of the answer, and the sum of the Y components of F1, F2, 3, and F3 is the Y component of the resultant vector, as given by this formula. And as we saw, the magnitude of the resultant is the sum of the square of frx and fyx. There's a bracket missing here, my apologies. And the angle, the tan of the angle, is given by the ratio of the y component of the resultant to the x component. Now, how many of you have seen this kind of thing before? Have you? Yeah, put your hands up. That's good. That's the right answer. Abhinav, did you have a question? And Nicole? Oh, you're all putting your hands up to say you've done it, not that you have questions. Okay. All right, let's continue. So here is what I showed before in steps. I don't think I'm going to go through those in detail because you've seen this before. What I will do is give you a little question. Which vector below shows the sum a plus b? Is it the first guy, the second guy, the third guy, or the last guy? And you can see it there. Is it 1, 2, 3, or 4? I will now open the question. Text 2578 and your response. All righty. Well, let's see what we got. Item D, vector number 4, is the favored answer. Let's look at this. If we have A and B, B's pointing down, so it's not going to be number 3, which is up. It's clear that we've got a lot of horizontal component in the rightward direction, so it better not be number 2 or number 1. So almost by process of elimination, the correct answer has got to be number 4, which we see was pretty good here. Okay. Here's another one. Which vector below shows the sum? And is it 1, 2, 3, or 4 as per the answers? A, except the sum is now A minus B, so it's actually the difference, A plus negative B. So is it 1, 2, 3, or 4? Go. Okay, and we are done. Now let's see, before I show the answer, what is it going to be? Now I'm taking A minus B, so I'm adding an upward pointing vector. So presumably it's going to point up even more. That looks to me like it might be number 3, and it is indeed number 3. Very good. Okay. Now, we not only add vectors, we actually can do multiplication with them. And the simplest kind is when we multiply it by a scalar. And we can think about that like this. Suppose you add a vector to itself. Well, then you should get a vector that points in the same direction, because you haven't changed the direction, but it should be twice as long. F plus F should be a vector twice as long as F, or 2F. But we would get the same thing if we took the original F and multiplied it by the scalar 2. And we can do this as many times as we like, n times altogether. If I added a vector to itself n times, that would be like multiplying by n, where n is 2 or 7 or 20 billion. So we can generalize this process, multiplying not just by a positive integer, but by any scalar, a negative number or a fraction or anything we like. So the magnitude of A times F is the magnitude of A times the magnitude of F. And if A is positive, then AF will have the same direction. But if A is negative, then we flip the direction. If we multiply F by -2, we'll get -2F, which is a vector twice as long as F, but in the opposite direction. And if A is 0, then we get a vector that has 0 magnitude, which of course cannot point anywhere. It will not have a direction. We say that F1 and F2 are opposite vectors if they're the same magnitude but point in opposite directions, as in the picture here. So if we added these together, we would get 0. So far, so good. Any questions? Not seeing any. Let's keep going. So F1 minus F2, as we saw in that little online question, is like F1 plus negative F2. So if I want to subtract the green vector from the blue vector, I can do it by flipping the green vector backwards and then adding the blue to the flipped one, which here is colored purple. And we can either do this with the parallelogram method or the triangle method. It doesn't really matter. I like the triangle, and the way I would do it is I put the tails together, but then I follow the subtracted one backwards to the tail and then forwards on the positive one. And I will get this vector. Same as parallelogram. Either is an acceptable method. So let's test you. Yes, go ahead.
Why didn't we put the vectors from head to tail instead?
Well, I could have if I had, let's go, I'm trying to go to the previous slide. Why won't it do it? All right, let's just do this. It's not letting me go backwards. I could do it that way. If I wrote the subtracted vector as negative F, then that's what the parallelogram thing is doing. It's adding it up. In a parallelogram, it's adding F1 plus negative F2. And the same will also work for the triangle method. So yeah, you could do it that way. All right, which shows this sum? Here are the 4 pictorial choices. C minus twice this little guy. Is it 1, 2, 3, or 4? I'm opening the question. Time is running out, but we are still getting, okay, they're coming in fast and furious. And we're done. Now, if I look at this, D looks like it's about half of C, so twice D looks like it's the length of C. If I added them, I should get something pointing this way, which looks like number 4. But I'm subtracting, which means twice D is going to point up this way. So it looks like it's going to give me number 1. And that looks like the majority answer, which is indeed correct. Very good. Okay. Now, we use very often what is called Cartesian vector notation. And we're going to use it a lot in this course, but you will be introduced to other kinds of notation, polar notation. But for now, let's look at Cartesian. So, a Cartesian axis, it's named after Descartes, basically is where we imagine that if we're making measurements relative to some reference frame, we have 3 rulers placed perpendicular to each other. And one ruler, straight line, is what we would call the x-axis, another the y, and another the z. And we can imagine unit vectors, vectors of length 1 in whatever units we're using, and pointing along each of these axes. And we typically call these I hat, j hat, and k hat. Sometimes they're called x hat, y hat, and z hat. So any vector in 3 dimensions can be written like so. We have f, some vector f, is something times I hat, that's the x component, plus something else times j hat, that's fy, or the y component, or something else times k hat, which is fz, or the z component. And there, as I said, the usual scalar vector, what that means is the vector components, which are quantities of magnitude, hence scalars. But basically, if you want to write out the components in a formula, this is the way to do it. That's the utility of the Cartesian notation. And it's very helpful because you can do this for lots of vectors, write each one in terms of x hat, in terms of I hat, j hat, and k hat, and then you just collect all the like numbers together, as in this next set, and then you get the answer, which is here. As we see, the resultant vector, the x component, is the sum of the x components of the original individual ones, f1 to fn. The y component is the sum of the y components, fy1 to yn, and likewise for z. All right, another little question. Here's 2 vectors, 3i hat plus 3j hat minus 5k hat, and negative 3i hat plus 6j hat minus 5k hat. Which vector below gives the sum? A, B, C, or D? You're adding them up. Remember, you add components. Go for it. Okay, very good. So let's see. If I add these components, I see that I get 3i hat minus 3i hat is 0i hat. So the answer better not have I hat in it, and there's only one answer that does, and that's A. And indeed, A is correct. And basically all of you got that. Good work. Okay. So position versus displacement. Matthew's going to talk about that more at the next class. A position vector describes where a point is relative to the origin. So if you have some point, x, y, z, xa, ya, za, then you can write its position as just xa times I hat plus ya times j hat plus za times k hat. But a displacement vector is the position of some point B relative to another point A, in which case you subtract the B position vector, you subtract the A position vector from the B position vector like so. So here it is in pictures. Here is vector A. Here is vector B. This is the position of point A. This is the position of point B. The displacement vector is the red vector, which is B minus A. And to do what I said before, I start from the vector being subtracted. I go backwards to the tail of the other one and then go forwards, and the answer is the red guy. So here is a 2D displacement example. Suppose R1 is at the point 32 in units of meters, and R2 is at the point 4, -3 in units of meters. There they are in the picture. So if I add these two together, I'll get 7 meters I hat minus 1 meter j hat, as you can see. 4 plus 3 will give me 7. 2 minus 3 will give me -1. Notice the units, meters, meters, everywhere in each term.
Professor, can you please explain the displacement vector again?
If the displacement vector is the relative position of one point compared to another. So the displacement, I'm going to do it here. The displacement of this point relative to that one is given by R2 minus R1. The displacement of this point relative to that is R1 minus R2. And that's what I've got at the bottom. The relative, the displacement vector of this point at the end of this arrow compared to that one at the end of that arrow is given by taking this guy and subtracting R2 from it. So I can just do that by taking 3 minus 4, which is -1, and 2 minus -3, which is +5. And that is the answer. And there's the displacement vector right there. Minus R2 plus R1, that displacement points here. Notice this vector, if I put it at the origin, is at the origin, but if I slide it over, it will give me this displacement, because it's, if I put its tail at the end of R2, its head will be at R1. Sorry?
Yeah, sorry about that, sir. So I just wonder, is this displacement vector referred to like a vector like the tail is another, like it's linked by 2 points, or it's like two vectors?
It's simply, no, it's one vector that tells you the relative position of one point compared to the other. Aaron.
So when you're doing a displacement vector, you take the first one given to you, subtract the second one given to you, right?
Yeah.
Or like the first one given in the question and the second one given in the question?
Yes.
It's not the other way around? Okay.
Yeah. Be careful to read the context, but yes, that's right. Here's twice R1, which is pretty easy. You just multiply each component by 2, so you get 6 meters I hat plus 4 meters j hat. The magnitude of a vector we've already seen is the square root of the sum of the squares of its components, and there's supposed to be a dot here. It's the square root of the dot product of the vector with itself, and I'm going to close off by talking about dot product. To get a unit vector, take the original and divide by its magnitude, and for some reason the dots didn't come out on this slide, but this is supposed to be a dot A in the square root. So if I have, let's say, a vector v, velocity 2 meters per second I hat plus 1.5 meters per second j hat plus 0 k hat, the magnitude is given by taking the square root of 2 squared plus 1.5 squared, which turns out to be 2.5. And so the unit vector v hat is this vector divided by 2.5, which is this. 4/5 I hat plus 3/5 j hat. So you use trig to define the components. As we said before, a cos theta is the x component, a sine theta is the y component. I'm not going to belabor that point because we've seen it already. I want to close off with dot and cross product because we'll use these a lot. The dot product, or scalar product, is a scalar quantity that represents the product of the magnitudes of a vector and the component of another vector projected onto it. Basically, it's the product of the magnitudes times the cosine of the angle between them. How many of you have seen dot product? Yes, lots of you. How? You have a question. Okay, you've all
Yes,
raised
sir.
your hand. Yeah, go ahead.
That you were talking about displacement vector. It's another one called position vector, right?
Position simply is the displacement relative to the origin.
Okay.
Think of it that way.
Okay. Thank you, sir.
Okay, so the nice thing about dot product is you can either use this formula or you get it by multiplying the x components together, adding them to the product of the y components, and adding that to the product of the z components. Both of these formulas will give you the same answer, and if you calculate it both ways and get a different answer, you've made an error. Because mathematically, you can show they must be equal. So if I write this out using this Cartesian method, then this dot product, A dot B, I don't know why the dots aren't coming through, I'm sorry, is AX BX plus AY BY plus AZ BZ, and that's B dot A. The dot product of two vectors is a scalar, and you can see from this little triad, I hat dot I hat must be 1. It's a unit vector. J hat dot J hat must be 1. It's a unit vector, and K hat dot K hat must be 1. But they're all perpendicular to each other. The angle between them is 90, so the cos of the angle between them is cos of 90, or 0. So therefore, I hat dot J hat is 0, J hat dot K hat is 0, K hat dot I hat is 0. So that's why this is useful, in using these relations, you can see how multiplying this together means I just dot I hat to get this, J to J to get that one, and K to K to get that, and add them together. There are two useful rules. A dot B plus C is A dot B plus A dot C. And if A dot B is 0, A and B must be perpendicular. So here's the longhand version of this thing here. I'm not going to work it out in detail. Well, actually, I have on the slide. I'm not going to say it in detail. If you multiply this out by brute force, you get these 9 different terms. But because of these relations, 6 of them vanish, and 3 of them give 1. So there's the vanishing. I love doing this. So much fun. Those guys all vanish by this second equation, and the other ones give unity by the first equation, and so as a consequence, we get this product here, which is, I don't know why this thing isn't coming up on the screen, but anyway, there we go. So a dot product of two perpendicular vectors is 0. A dot product of two vectors of given magnitudes is greatest when they're parallel to each other, and it's smallest when they're anti-parallel, because you'll get a negative number. Joel, what do you want?
Thank you. Just to clarify, the dots are just like in between like the different variables, like A, X, and BX.
Yep, component by component. AX, BX plus AY, BY plus AZ, BZ.
Okay, thank you.
And dot products, as I said, are commutative. A dot B is B dot A, which is AB cos theta. And I've got a bunch of pictures here that I'll let you look at later so you can visualize how this works. I'm going to finish with cross product. The cross product of two vectors defines a vector that's perpendicular to both. So A cross B is a vector, and it's a vector that points perpendicular to both of the other two, and its magnitude is A times B times the sine of the angle between A and B, as compared to the cos. So you can also get this in Cartesian, and it's a bit more complicated. The x component is AYBZ minus AZBY. The y component is AZBX minus AXBZ, and the z component, or k-hat component, is AXBY minus AYBX. We'll be using cross products later in the course when we discuss rotation. How many of you have used or seen cross product before? Put up your hand if you have.
Yeah.
Yeah, lots of you? Some of you? Yeah, lots. Okay, good. Was there a question?
No, I had a question, but I answered it myself.
Okay, good. Best kind of question.
Mr. Mann, can you please explain the cross products again?
Okay, it is a vector that is given by this formula. The magnitude is AB sine theta, and its direction is perpendicular to both to the plane traced out by A and B, or perpendicular to both A and to B. That's the definition. If you imagine, put your index finger and your middle finger perpendicular to each other, and then raise your thumb. Your thumb is like the cross product of your index with your middle, except maybe for the magnitude, but that is how you get the direction, provided you use your right hand. Are there questions here? Tarek, did you have a question? No? Yes? Matthew? Yeah, okay, go ahead. Whoever it is, yeah.
It's Tejas, hi. So
Tejas, hi.
Hi, would the, let's say the direction of the cross product vector, if it was something like a linear system, I mean, things that are perpendicular are usually like reciprocal slopes, right? So how would you say its slope is in relation to the AB?
Well, I'm not sure what you mean by the slope in relation to AB, because it would depend on the slope. The best thing I have is this visual picture. It's always perpendicular to the two vectors going into the cross product, no matter what. That's the definition.
Okay, so you would try kind of just like flip the slopes like you do for other like linear things, but I guess in a different way. I'm not really sure how this one works, but.
Okay, I see several questions. Arya?
Could you just quickly repeat the definition of a dot product?
The dot product is AB cos theta. Magnitude of A times magnitude of B times the cos of the angle between them.
Okay, thank you.
Christopher?
Would a cross product exist if A and B were perpendicular?
Yeah. It does not exist when A and B are what?
I'm not sure.
Parallel.
Parallel. Rather it exists, but you'll get 0 because the sine of the angle between parallel vectors is 0.
But I thought two perpendicular vectors resulted in 0.
Pardon me, you thought what?
I thought two perpendicular vectors resulted in 0. Like when you multiply
only
them.
Only for a dot product. For a cross product, they give you something.
Okay, I see. Thank you.
Arvind? No, Matthew? Matthew Stablinski?
Yeah.
Or Stabelsky, sorry.
it's you pronounce it pretty well. But so I was wondering, so the cross product is like pretty tangible. What you know that you're getting the parallel vector of both vectors A and B. But what I'm wondering is like
perpendicular vector, but go on, yes.
Sorry. But I was wondering like what is the tangible, what does a dot product do, and like how, like I know it's the magnitude of A and B.
What does it mean? What's it going to mean? It's going to mean rotation. Think of this. If you have a merry-go-round and you want to push it, do you push it toward the center or do you push it perpendicular to the center? What's the way to get a merry-go-round to go around?
Perpendicular to the
Right. And that is where we need cross product, because the harder you push it, the more it will accelerate around. But no matter how hard you push it to the middle, it's not going to rotate. And this is why you need cross product, and that's where it's going to come in. Now, I see other questions. I'm going to go on and show you a bit more, and then I'll take some more questions, okay? So this is the right-handed rule. To get the direction of the answer, point your index finger in the direction of the first vector, your middle finger in the direction of the second, and wherever your thumb goes of your right hand, that's the direction of the third one. Or another way of looking at it is place all your fingers in the direction of the first guy, then curl your hand in the direction toward the second guy, and wherever your thumb goes, that's where the answer is pointing. Use your right hand. That is called the right-handed rule. So before I take questions, I'm going to remind you, magnitude of the cross product actually corresponds to the area of the parallelogram that has vectors A and B on its sides. And as we noted earlier, the cross product of parallel vectors or anti-parallel vectors is 0. Now, one more thing, and then I'll take questions. The magnitude is greatest when the two vectors are perpendicular to each other, and unlike dot product, cross is anti-commutative. A cross B is the negative of B cross A. What does that mean physically? Well, think of pushing a merry-go-round. If you push it one direction, it rotates one way, but if you turn around and push it the other way, it will rotate backwards. That backwards motion is this minus sign. Okay, any questions? Some of you had them. Maybe I answered them in this. Eden?
Yes. Will the slides for chapters 1 and 2 be posted on Top Hat?
Yeah, we'll do that real soon. I'll do it either later tonight or by tomorrow. Probably tonight. Joshua.
Okay, thank you.
Yep, Joshua, and then Aaron.
Yeah, my question was basically just what time on Tuesday is the quiz?
8:30 p.m.
Okay, perfect. And also, I was just wondering what chapters will the quiz be on? Is that just the first couple chapters?
These first two.
Awesome.
Mostly chapter 2. It's a practice quiz, mainly to get you used to using the quiz facilities in Mobius and to brush up on what you know and what you don't. But this one will not count toward your final grade.
Perfect.
Aaron.
Is there, sorry, I just have one more question.
Go ahead. Yeah.
Questions on Top Hat to do as well?
Well, they are already there in the textbook.
Right. Okay. Perfect. Yeah.
Okay, Aaron.
Thank you.
Would you please go to the previous slide? I just didn't quite copy it down. Thank you.
Okay, Mario. No, Mario? Okay.
No,
yes?
my question was this one. It was to go back to the slide.
You guys can go back in the slides in the Top Hat.
Yeah, you can do it there. I think I want to go on and finish. I have basically almost nothing left, and I'm conscious of the time. We've gone longer than I thought. Here is what cross product looks like as a formula using the Cartesian notation. The cross product of two vectors is a vector. It has magnitude and direction. And it's kind of the opposite of dot. The I cross I is 0, j cross j is 0, k cross k is 0. The cross product of a vector with itself is nothing. And because these guys are perpendicular, you almost can see I cross j is k, j cross k is I, and k cross I is j. So if I can make use of these useful rules, A cross, the sum of vectors is the sum of the cross products. A cross B plus C is A cross B plus A cross C. And if the cross product vanishes, the vectors are parallel or anti-parallel. So here's A cos theta I hat plus A sine theta J hat. Here's B, A cos theta B plus I hat plus B sine theta B J hat. And here I grind out the whole thing for you. And at the end of the day, where's this vector going to point? Can anybody make a reasonable guess? Yeah, where? Somebody say it. A and B are in the IJ plane, so it's got to be perpendicular. It's got to point in the K hat direction. And it does. And actually, if you work it out and use a trig addition formula, you do indeed get AB times the sine of the angle between them, which is the sine of theta B minus theta A.
Mr. Mann, I have a question.
Yep, go ahead.
So how do you do angles in 3D? I've never done that before.
Well, I do it like this. I remember these rules, I write it out in Cartesian, and I apply the rules. That's how I did it here. I see other questions. Let me, I'm going to put up that for you to look at. Ian, did you have a question?
Yeah, so you said the first quiz was next Tuesday at 8:30. I have a lecture tutorial starting next Tuesday at 8:30. What should I do?
Well, what we're going to do is give a window around that time. At yours is at 8:30 p.m., is that right?
AM.
Oh, well, the test is at p.m., 8:30 p.m. That was cleared with engineering. No, none of you should have a conflict. p.m., 8:30 in the evening. Okay, anybody else? Parth.
Yeah, I just had a question about assignment 0.
Yeah.
Is that for marks or is it more of our own practice?
I believe it will be practice.
Okay, for sure.
Yeah.
Thank you.
Eden.
Where can we access assignment 0?
We'll send information about that soon in an email, okay?
Okay.
Joshua.
Oh, sorry. I think my hand's still up from earlier. My bad.
All right. All right. I'm trying to finish. Jess, did you have something?
Yeah, I'm just wondering, is chapters 1 and 2?
That's right.
Those won't be on any tests or exams or assignments, right? Like real.
Basically, after this, no, but they're very important background for the stuff that will be on tests and quizzes. Yes.
Okay. Thank you.
All right. I'm going to give a question, and then that pretty much finishes the class. Here's two vectors, 2n hat plus 1 Newton j hat. It's a force. And that's one vector. The other vector is 1 meter j hat. What's the dot product? Is it minus 1 Newton meter, 1 Newton meter, 2 or 3? Go. Okay. Well, F dot R. I hat dot J hat is 0, so this won't give anything. J hat dot J hat is 1, so it looks to me like the answer is B. and it is. It's 2n I hat plus 1n j hat dotted into this. You use a plus a dot b plus c is a dot b plus a dot c, and you get the dot of this with this is 0, the dot of this with this is 1, and that's why you get 1. So one more of these things. What's the cross product of these guys? Is it -2, -1 k hat, 1, or 2? Remember, A cross B plus C is A cross B plus A cross C, go. Oops, go. Here. Why did it say stop answering? I'm going to go back. Something went wrong with that guy. I want to go backwards, but it won't let me do it. Okay. Oh, that's way too far back. All right. Let's just... All right. Let's try this again for cross product, okay? I'm going to open the... It's not letting me do it. Why is it doing that? This is really proving a bit nasty here. Maybe I'll just have to can that question if I can't get these guys to cooperate, which it looks like I cannot. So I think maybe we'll just have to stop here and not count that last question. We're already well over time. Are these hands up representing questions, or did you guys just forget to put your hands down?
Mr. Ryan, I have a question.
Yeah, go ahead, Mario.
So for Friday, are we going to start chapter 3 or?
Yes.
Okay.
Javier? Nope, not hearing anything.
Yeah, sorry.
Oh, go ahead. Yep.
Yeah, so for future reference for different chapters, like for the chapter 3 test and the chapter 4 test, like we're not going to have any of this stuff on it, or?
Oh, a lot of it'll be on it, but you'll
okay.
have to use it, and you'll
Right.
see how that unfolds in the course.
Okay.
But the first quiz is about this stuff, and assignment 0 is about this kind of thing to give you practice. Zongyan?
Oh yeah,
Jason?
yeah. Just wondering if this meeting will be post-inner.
Pardon me?
Oh, just wondering if this meeting record will be post-inner.
Yes.
Okay.
Daniel?
Is there any additional practice we can do other than the assignment 0?
Well, there are the problems in the text, and there are lots of them. They appear in there, and you should give them a try. In the first tutorial, they will review this material with you, and you'll have some practice questions there as well. The first tutorial's this coming Monday. Darsa?
So for the lecture on Friday, is there any reading that we need to cover beforehand?
Chapter 3.
So, Mr. Mann, will the chapter 3 PowerPoint be posted, or?
I expect so in the near future. Matthew is working on it.
Will it be posted before Friday?
Yeah, chapter 3 is posted on Learn with any typos that... Sorry, chapter 3 is posted on Toplot with any typos that might be present right after this. Before I go to bed sometime tonight, I'll post the chapter 3 PowerPoint on Learn.
Thanks, dude.
Okay, I'm going to have to close this down pretty soon, but I see a lot of questions. Sinan. Is that how you say your name, Sinan?
It's Sinan, but I just had one quick
Sinan,
question.
okay,
So
sorry,
I just wanted-
Sinan, yes.
It's all good.
What can I do for you?
One clarification. So for so we're supposed to have chapter 3 reviewed by Friday, but for Tuesday it's only going to be chapter 1 and 2, mainly 2, correct?
Yeah, chapter 3 starts Friday, and it will go through all next week, chapter 3. We did the first 2 chapters today quite quickly because this is all supposed to be review material. But now some of chapter 3 will probably be reviewed to some of you, but chapter 3 is going to occupy Friday and next week as well, I believe. Is that right, Matthew?
Chapter 3 and chapter 4. They're kinematics in 1, 2, and 3 dimensions. So it's basically the same thing, just living
More
in a
dimensions.
3-dimensional world instead of the easy 1-dimensional world.
So 3 and 4 are the next 3 classes. Chapters 3 and 4. Vincent.
Sir,
Yep.
I'm having trouble logging into Mobius. I don't know if anybody else is having that issue. I did register and use the access codes that were provided like with the bundle, but when I try to log back into it from like the top hat, it's not exactly working anymore.
Okay, I don't know why that is. I try to do a hard refresh, but that's a question for the OLAs. Send an email to the Phys 115 email and they will get back to you.
Okay.
Or maybe other students I see putting stuff in the chat. Anybody? Varished.
Hi. Will a cheat sheet be allowed for the quiz on Tuesday with the formulas for the cross product or the dot product that we can write?
Okay, the way the quizzes work and the tests is you will get no help sheets whatsoever because you can make your own. They're online and you can consult whatever you want, but the constraint will be that you must handwrite your answer and resubmit it. And that will consume time. So your optimal strategy is to learn the material and write it right away instead of hoping you're going to find it on the internet with hunting. Because for every minute you hunt, that's one less minute to write by hand.
So, sir, are you saying this is like their open book then?
Basically, yes.
Okay, but like don't copy it because we're gonna you waste too much time if we don't know the material.
Well, I mean, I won't accept anything but handwritten answers.
Sure.
And we also have online assistants checking the internet. And if an answer is too close to what is on the internet, a person will be investigated under policy 71.
Sounds good.
Okay? Boy, questions. Jade. Jade?
Hi, just wondering for the handwriting test, can we use tablets or something else rather
You
than...
can handwrite it on paper and scan it, or you can handwrite on a tablet, but it must be handwritten.
Okay, thank you so much.
Aaron.
So we can, like, for example, if there's something that we feel that we'll need a reminder for on the quiz, we can write our own little like help sheet beforehand, and that won't waste too much time. Like, we're allowed to do that?
No, you can write it all beforehand. I view that as part of the learning process for you to write these help sheets for yourselves.
Okay, and we can use them on the quiz.
Sure.
Okay.
Alex. Yeah. All right.
No problem as well.
Okay, write down what the problem is, and if you could add a screenshot to the email, that's fine, and we'll get on that right away with the Top Hat people.
Another solution, if for some of you who might have a Mobius, you can also enter your answers into the Mobius system. That might give you a little better formatting. Similar to Top Hats, like completing the problems at the end of the chapter aren't necessarily for marks unless it's part of like the official graded assignments.
The other thing I've been told is I think Google Chrome is the optimum browser to use.
Yep, Google Chrome and possibly Firefox. Stay away from Safari.
So that might help. But in any event, if you want to try that again and it helps, or what Matthew said is fine, but if not, write down in a simple way what the problem is, send it to the 115 email, we'll look into that. Vardman. Vardman?
So since you said the tests are going to be almost open book, will we be allowed to use your notes for tests?
Whatever you want.
All right.
But keep in mind, it takes time. So effectively, yeah, they're all open book.
Okay.
But you will be asked to do calculating and deriving, and there's a limit to how much an open book is going to help you with that. The reason for this else. And I have taught that this method seems to optimize a person actually learning the material instead of cheating. And I can't prove that for sure yet, but I have found the averages in courses where I have done it this way in the online world are the same as when we didn't do things online. Cheating is time consuming, especially if you have to write out the answer in a way that we can't recognize. That is very costly time-wise. Do not be fooled. But none of you would ever cheat. Vij.
This a special 8 p.m. Meeting was just a one-time thing, right? Since
Yes.
we wanted to cover the
Yeah,
review.
we're back on track. It was just today because of the screw-ups earlier. That's correct.
Okay,
Mr. Mann.
Oh, I just had a really quick follow-up. So today's I had to come a bit late. So today the 8 p.m. meeting just covered chapter 2, right? Chapter 1 we considered.
Well, a little bit of the end of 1 because I thought I did it quickly, but chapter 2, yeah.
Okay, thank you.
Mr.
Alex.
Mann.
Sorry, Alex is next. Alex Kelk.
Yeah, I was just wondering, how long do we have for the quizzes once we start them?
That will be announced in the near future. The time scale will probably be on the order of 60 to 90 minutes.
Okay, thank you.
Who else is there? Christopher Maniz?
Yeah, so within that time frame of the quiz, is submitting like our photos of our work, is that like included in the total time, or do we get extra time for that?
It'll be the total time, which is why they might be a bit longer, but it will include upload. I mean, the total time will include the upload time.
Okay, and just a quick question: when's assignment 0 due?
That's a good question. Probably a week Sunday. I mean, it doesn't count, so the due date doesn't really mean anything. But we will clarify that in the near future. We haven't worried about that because it doesn't count much. Boy, you guys have a lot of stamina. Roy.
Yeah, hello. My question is that if we purchased access to Top Hat directly through Top Hat, do we also get access to Mobius, or was that only in like the bundle? Yes.
Yes, but you have to actively join, but it is included. Yes.
All right. Well, yeah, I think I'm having like issues joining.
This guy, look at this.
My like access, it says that it's limited and that it will expire within like a few days. So that's why I'm asking.
Okay, take a screenshot, send it to the 115 email, and we will have people look into it.
All right, thanks.
Okay, I'm really, How, did you have a question?
Yes, sir. May I check our class schedules with you?
Sorry, I didn't hear. What?
May I check our like class schedules with you? Because like I was really confused about our schedules. Like,
okay, do that offline in an email to 115 because I don't want to waste everybody else's time. But sure. Who else is left? Jess?
Yes, sorry. I just want to confirm, will there be the PDF ready for chapter 3 before the class?
Matthew, I think so, won't it?
Yep, that's on my to-do list tonight.
To like download and write on?
Yep, that'll be on Learn.
We're on it.
On Top Hat, you can only see the slides.
It'll be on
okay. Mario.
Yeah, my question is quick. It was just that the quiz on Tuesday, is it getting marked or is it just like assignment 0?
Doesn't count. It's a it's a trial run of a quiz, but after that they will count. Vardman.
Oh, sorry, I forgot to put down my hand.
Okay, good. Anybody else? Vij, you had your hand up. Is that because you forgot?
I'm so sorry. Yeah, I did. Good night.
Okay. I see Curty. Curty?
Hi, yeah, I just had a question regarding the class voting. In the morning, I got kicked out of the Zoom meeting, and so it caused me to get some, like, I had to randomly pick some answers because I wasn't able to see the questions on Top Hat.
Yeah, well, the things are bonus. If you had a problem, let us know, and we're going to try and take that into it. Well, we're going to take that into account when we calculate the bonus things. Because what happened today was not the fault of any of you people.
Okay, and the questions even during this session are counted as well because I joined late.
Yeah, they are, but they're bonus. They're bonus. And keep in mind, we'll have lots over the course of the term. So, it affects Epsilon. Okay, all right, I think it's time for me to call an end to the meeting. I thought this meeting would be 40 minutes, but there are so many questions. It's longer. It's great to see the interest. I hope you enjoy the course. Physics is a very interesting subject and very useful in all kinds of engineering disciplines. And we hope you get a lot out of it. And again, my apologies for the mix-up today. But don't let that discourage you. Take care of yourselves, and I guess the next session will be Friday. Bye-bye, everybody.
Thank you.
Thank you, sir.
Thank you.